In this lecture, we want to look at the stack and then proceed to subroutines. A stack is an area of memory that has been reserved for access as a last-in, first-out storage area. This means that the last item stored on the stack is the first item to be removed from the stack. Removing an item from the stack does not mean that the contents of the corresponding memory location are deleted. All it does is to read the contents of the memory location and then invalidate the location as a location on the stack. Whenever a data item is added to the stack, it is stored in the memory location that follows the location that holds the last valid data item on the stack. In the illustration, base is the starting address of the stack and top is the address that contains the last valid item on the stack. When items are added to the stack grows, and when items are removed from the stack becomes smaller. Microprocessors have a register called a stack pointer. The purpose of the stack pointer is to store the address of the last valid item on the stack. In other words, it points to the top of the stack. When an item is added to the stack or an item is removed from the stack pointer is adjusted accordingly so that it remains pointing to the top of the stack. Depending on the microprocessor, a stack can grow upwards or grow downwards. For a stack that grows upwards, new items added to the stack are stored in higher addresses. This means that as items are added to the stack pointer increments. For a stack that grows downwards, new items added to the stack are stored in lower addresses. This means that as items are added to the stack pointer decrements. Adding an item to the stack is known as pushing. When an item is pushed onto the stack, it is stored in the first free location that follows the location that holds the last valid item on the stack. The stack pointer is updated. That is, for stacks that grow upwards, the stack pointer is incremented, and for stacks that grow downwards, the stack pointer is decremented. Removing an item from the stack is known as popping or pulling. When an item is popped from the stack, the item at the top of the stack is retrieved. The stack pointer is updated. That is, for stacks that grow upwards, the stack pointer is decremented, and for stacks that grow downwards, the stack pointer is incremented. Let's illustrate operations on the stack using a simple pseudo microprocessor. Shown are contents of registers that we want to work with. These are the stack pointer SP and the general registers A, F, B, and C. The microprocessor has a stack width of 1 byte. This means that items are pushed and popped as bytes. Let's suppose that the stack grows downwards. At the present moment, the stack pointer contains 8058. This means that the address of the last valid item on the stack is 8058. Memory locations whose addresses are above 8058 contain valid stack items. Memory locations whose addresses are below 8058 contain invalid stack items. If A is pushed to the stack, the contents of A are stored in memory location 8057. This is a location that follows the last location that contains valid stack data. The stack pointer is decremented from 8058 to 8057 so that it points to the new top of the stack. If F is pushed to the stack, the contents of F are stored in memory location 8056. The stack pointer is decremented from 8057 to 8056. Let's suppose there are some activities that change contents of A and F to 32 and A8 respectively. Then, after those activities, if we pop into F, the contents of memory location 8056 are loaded into register F. The stack pointer is incremented from 8056 to 8057. We can see that we have restored the contents of register F. If we pop into A, the contents of memory location 8057 are loaded into register A. We can also see that we have restored register A. The stack pointer is incremented from 8057 to 8058. If we pop into C, the contents of memory location 8058 are loaded into register C, and the stack pointer is incremented from 8058 to 8059. If we push B to the stack, the contents of register B are stored in memory location 8058, and the stack pointer is decremented from 8059 to 8058. Generally, the stack is used to store data that requires access on a LIFO basis. But let me give the following two important uses of the stack. Number one, to store return addresses when branches to subroutines or interrupt service routines are made. We shall be looking at subroutines in a moment. Number two, to pass parameters between program routines. You can think of these program routines as functions in the C programming language. You should be able to recall that parameters are passed between functions as function arguments. In the actual microprocessor, the calling routine pushes the parameters to the stack. The called routine can then access the parameters from the stack. Let's zoom in on the 8086 stack. The 8086 stack is contained in the stack segment. It grows downwards and starts from the highest address in the stack segment. The stack pointer is 16 bits wide and contains the offset of the last item on the stack relative to the base of the stack segment. The base of the stack segment is the lowest address in the stack segment. The 8086 has a stack width of 16 bits. This means that it pushes and pops data as 16-bit values. Since memory addresses are addresses of 8-bit quantities, two consecutive memory locations are accessed on each push or pop. A push decrements the stack pointer by 2, and a pop increments the stack pointer by 2. GPRs, segment registers, and memory contents can be pushed to or popped into from the stack. This is an illustration of the 8086 push operation using word equations. For a 16-bit value pushed to the stack, the higher byte goes into the memory location pointed to by SP-1, and the lower byte goes into the memory location pointed to by SP-2. SP is decremented by 2. We notice that for the two memory locations accessed by the push operation, the higher address contains the higher byte and the lower address contains the lower byte. Also, we notice that after the push operation, the stack pointer points to the address of the lower byte. For the pop operation, the memory location pointed to by SP is loaded into the lower byte, and the memory location pointed to by SP plus 1 is loaded into the higher byte. The stack pointer is incremented by 2. I recommend that you do these questions from chapter 6 before you proceed to the next section. A subroutine is a sub-program which can be branched to from another program. The program that is branched from is referred to as the calling routine. On the completion of the subroutine, execution branches back to the calling routine. Branching to a subroutine is effected by a call instruction in the calling routine. Branching back to the calling routine is effected by a return instruction at the end of the subroutine. Let's illustrate the execution flow in a program that contains subroutines using the example program shown. The program begins executing from address 0850H and proceeds sequentially until address 0853H when it encounters a call instruction. The call instruction causes branching to address 0861H. In other words, it causes branching to the subroutine located at address 0861H. From 0861H, execution proceeds sequentially until address 0865 when a return instruction is encountered. The return instruction causes branching back to the calling routine. It causes the branching to land at address 0854H. From 0854H, execution proceeds sequentially until address 0858 when another call instruction is encountered. The call instruction causes branching to the subroutine located at memory address 0866H. From 0866H, execution proceeds sequentially until address 086B when a call instruction is encountered. This call instruction causes branching to a subroutine located at memory address 0870H. This subroutine is a subroutine that has been called inside another subroutine. It is referred to as a nested subroutine. In theory, as many subroutines as can be supported by the stack can be nested. From address 0870H, execution proceeds sequentially until address 0875 when a return instruction is encountered. The return instruction causes branching back to address 0860H. From address 0860H, execution proceeds sequentially until 086E when another return instruction is encountered. The return instruction causes branching to address 0859H. From address 0859H, execution proceeds sequentially. If more call instructions are encountered, they are going to be handled in the same manner as the call instructions that we have already seen. The diagram that we used to show the example program made it appear as if the calling routines and the subroutines are in different memories. In reality, they are all in the same memory, as illustrated in this diagram. In the 8086, calls and returns can be classified as near or far. Near calls and returns are calls and returns to addresses within the same segment. Only the call or return offset needs to be specified. Far calls and returns are calls and returns to addresses in another segment. There is need to specify both the call or return offset and the segment selector of the target segment. Let's illustrate the near call instruction using word equations. When a near call instruction is executed, the higher byte of the instruction pointer IP is stored in memory location pointed to by SP-1. The lower byte of IP is stored in memory location pointed to by SP-2. SP is decremented by 2. In other words, the instruction pointer is pushed to the stack. Pushing the instruction pointer to the stack is used to preserve the address of the instruction that follows the call instruction so that program execution can be able to branch back to that instruction. To branch to the required subroutine, the starting address of the subroutine, called the call address, is loaded into the instruction pointer. The call address is specified as an operand of the call instruction. For the near return instruction, the contents of the memory location pointed to by SP is loaded into the lower byte of IP, and the contents of the memory location pointed to by SP+1 are loaded into the higher byte of IP. SP is incremented by 2. In other words, the return address is popped from the stack. This makes program execution to branch back to the instruction that follows the last call instruction. For the far call instruction, the word equations show that the code segment register followed by the instruction pointer are pushed to the stack to preserve the return address. To branch to the required subroutine, the segment selector for the target segment is loaded into the code segment register, and the offset of the subroutine in the target segment is loaded into the instruction pointer. The segment selector and the offset are specified as an operand of the call instruction. For the far return instruction, the equations show that the instruction pointer followed by the code segment register are popped from the stack. This makes program execution to branch back to the instruction that follows the last call instruction. I recommend that you do these questions from chapter 6 before you proceed to the next section. Input data required for the execution of a subroutine can be passed to the subroutine by initializing some registers or memory locations with the input data before calling the subroutine. The results of the execution of a subroutine can be passed back to the calling routine by storing the output data in some registers or some memory locations before leaving the subroutine. Alternatively, the stack may be used to pass in and pass out data between the calling routines and the called routines. This example illustrates the passing of data between routines using registers. The calling routine initializes registers DX and AX with the input data before calling the subroutine convert. When the subroutine executes, it carries out the operation that it is designed to carry out and stores the results of the operation in register AX. The calling routine can then access register AX and use the contents of the register for further purposes in the program. At times, it is necessary to preserve CPU registers when subroutines are called so that the registers can be used on return from the subroutine. To do this, registers can be pushed onto the stack as soon as the subroutine is entered. They are then retrieved by popping them back just before leaving the subroutine. Popping should be in reverse order to ensure that the registers are restored correctly. The 8086 has instructions that allow pushing and popping of all the GPRs at once. In the example illustration, the flags register and DX need to be preserved. To do this, the registers are pushed to the stack on entering the subroutine. Then the instructions in the subroutine are executed, after which the registers are restored by popping them back from the stack. Care should be taken not to change anything on the stack if one has incomplete information about the current contents of the stack. Otherwise, you will disturb the whole system. Let's look at some advantages of subroutines. Number one, subroutines can make programs to be modular. This allows build-up, testing, and debugging of software to be easier. Number two, subroutines can save memory space. For instance, let's suppose we have a block of 20 instructions that execute at 5 various points in a program. If not implemented as a subroutine, 100 instruction spaces are required in memory for the program. If the 20 instructions are developed into a subroutine, only 21 locations will be required for the subroutine. The 21st location is for the return instruction. 5 more spaces will be required for the calls at the 5 different places. The total memory requirement will be 26 spaces. Therefore, 74 spaces in memory have been saved. I recommend that you do these program development questions from chapter 6 before you proceed to the next lecture.